In this module, we'll be using game theory to analyze a social interaction between two individuals. The idea of a general theory of games was introduced by John von Neumann and Oscar Morgenstern in their famous book Theory of Games and Economic Behavior, which proposed that most economic questions could and should be analyzed as games. Within this assignment, we will consider a class of two-player normal form games in which the pursuit of self-interest leads to an undesirable outcome for both players. In the text, this type of social interaction is defined as a social dilemma. The specific game that we will consider is called a prisoner's dilemma, and it can be illustrated by a 2x2 payoff matrix, like the one that's on the bottom right of the slide. Normal form games are composed of three elements: 1, the set of players; 2, the feasible strategy space; and 3, the payoffs associated with each strategy profile. In this case, the set of players are defined as row and column, and they can be illustrated by these two boxes right here. The blue box indicates the row player, and the red box indicates the column player. The feasible strategy space for both players are the same for both players. Either row or column can either pick, cooperate, or defect. And in the payoff matrix, they are denoted right there in the blue and red boxes. The payoffs associated with each strategy profile are indicated by the numbers within the payoff matrix, which are just the integer values within the payoff matrix itself. Now that we have clearly defined all aspects of the prisoner's dilemma game, meaning that we know the number of players within the game, the strategies that each player can play, and the associated payoffs with each strategy profile, we would like to draw some inferences about the actual behavior of the players within the game given the defined aspects of the game. In particular, we would like to know what strategy would we expect each player to play and why. And there's a algorithmic process to go about figuring this out. First, I like to look at the column player and fix a specific strategy that the column player plays. So in this case, let's look at the strategy cooperate. So again, fix the strategy that column player plays as cooperate and see how row would respond to that fixed strategy. So in this case, row would pick defect because the payoff of 10 when he plays cooperate is less than the payoff of 14 when he plays defect. So I like to underline the strategy that the row player would play given that column plays cooperate. Second, I look at what happens when column plays defect. How would row respond given that column plays the strategy defect? And again, row would respond by playing defect because the strategy payoff would be 2, and 2 is greater than 0. Then I look at how column would respond given that row plays cooperate. In this case, column would be picking the strategy defect because the payoff of 10 is less than the payoff of 14. And lastly, I fix row strategy as defect and see how column would respond given that row plays defect. In this case, column would be picking defect because the payoff of 0 is less than the payoff of 2. Since we can see that we have two underlined numbers in the bottom right cell, this would be the strategy that we would expect both players to play, since this is the best response given what the other player is doing for both players. In this case, this is a social dilemma because the payoff of 2-2 is less than the payoff of 10-10 if they were to cooperate, which is by definition a social dilemma. Okay, now that we have seen that in a prisoner's dilemma game, the players would pick a strategy that is not socially optimal, we would like to introduce methods to induce players to pick the cooperative strategy that is socially optimal. So now suppose that row and column are somewhat altruistic, so each $1 received by the other player is worth 50 cents to them. rewrite the payoffs in the table to account for the player's social preferences. So in this case, we need to modify every combination of strategies: cooperate, 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 defect, defect, cooperate, and defect, defect. So we need to look at each specific cell almost independently. First, I like to look at the top left cell where both players are playing cooperate. So in this case, the payoffs are 10 for row and 10 for column. So if the column player receives a payoff of 10, if he plays cooperate, he gives half of that to the row player. So then the row player's payoff of 10 becomes 15. Conversely, the row player receives a payoff of 10, so he gives that half of that to the column player. So we rewrite that payoff as 15. Second, we look at the situation when row plays cooperate and column plays defect. So in this case, the column player receives a payoff of 14, and he gives half of that to the row player. So we rewrite the row player's payoff as 7. However, in this case, the row player receives a payoff of 0, so half of 0 is 0, and he gives 0 to the column player, so the column player's payoff remains the same at 14. Okay, now we look at what happens when the row player plays defect and the column player plays cooperate. So in this case, the column player receives a 0 payoff, so he gives 0 to the row player, and the row player's payoff remains the same at 14. However, the row player receives a payoff of 14, and he gives half of his payoff to the column player, so the column player's payoff is changed from 0 to 7. Lastly, we look at the strategy where both players play defect. In this case, since the column player is receiving a payoff of 2, he gives half of 2 to the row player, so the row player's payoff is changed to 3. And the same thing with the column player. The row player receives a payoff of 2, and he gives half of that, which is 1, to the column player, so the column player's payoff is changed to 3. Right? Now that we have figured out how the game has changed given altruistic preferences, we have to determine which strategies the players would play. So again, we kind of use the same algorithmic step that we did in this last slide. So assume that column player plays cooperate. How would row respond? Would he play cooperate or defect? In this case, he would play cooperate. Now assume that column player plays defect. How would row respond? Would he play cooperate or defect? He would play cooperate, right? Now fix row player strategy as cooperate. How would column respond? Would he play cooperate or defect? He would play cooperate. Now fix row player as defect, row strategy as defect. How would column respond? Would he play cooperate or defect? He would play cooperate. And since we have two underlying numbers, this is the best response for each player given what the other player is doing. And as we can see, both players would be picking the strategy cooperate, cooperate, and we have resolved the prisoner's dilemma by having altruistic preferences. Okay, now that we considered a situation where both players took in consideration the well-being of the other person to lead to a socially optimal outcome, we're going to return to the original assumption that the row and column are completely selfish. However, now assume that the game is played for 2 rounds, and that in round 2 both players play whatever strategy the other player played in round 1. In repeated games, this is called a tit-for-tat strategy. Rewrite the payoffs in the table to describe each player's payoffs over 2 rounds depending on the strategies that each player played in the first round. Okay, in this case, we're going to have to consider every combination of strategies again, where we have to consider cooperate, 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 defect, defect, cooperate, and defect, defect. So I like to focus on the on-diagonal entries first because intuitively they just are just easier. So let's focus on the situation where both players play cooperate, cooperate in the first round. Since both players are playing cooperate, cooperate in the first round, both players play cooperate, cooperate in the second round because each player mimics what the other player did in the first round, right? So the row player receives a payoff of 20 and the column player receives a payoff of 20. Second, let's look at when both players play defect in the first round. So if they play defect in the first round, they play defect in the second round as well because they just mimic what the other player does in the first round, right? So in this case, if you add up the payoffs in the first and second round, the row player receives a payoff of 4 and the column player receives a payoff of 4 as well. So now assume that in the first round, the row player plays defect and the column player plays cooperate. So since they mimic what the other player does in the first round, in the second round, that means that the row player would play cooperate and the column player would play defect, right? Because in the first round, row player plays defect and column plays cooperate. So in the second round, row plays cooperate and column plays defect, right? So then you just add up 14 and 0 for the row player and 0 and 14 for the column player, right, to receive the payoffs. Lastly, assume that in the first round, the row player plays cooperate and the column player plays defect. So in the second round, they play the row player plays defect and the column player plays cooperate. Again, you just add 0 plus 14 for the row player to receive a payoff of 14, and 14 plus 0 for the column player to receive a payoff of 14. Again, we use the same algorithm process to determine what strategy each player would play. So assume that column player plays cooperate. How would row respond? Would he play cooperate or defect? He would play cooperate. Now assume that column plays defect. How would row respond? Would he play cooperate or defect? He would play cooperate. Now assume that row plays cooperate. Would column player play cooperate or defect? Column would play cooperate. And assume finally that row plays defect. How would column respond to row playing defect? Would he pick cooperate or defect? He would pick cooperate. So we see that the best response for both players would be cooperate, cooperate, and we have resolved the prisoner's dilemma through repetition. Okay, in this last example, we're going to go over one final method to solve the prisoner's dilemma problem. So again, we return to the original assumption that row and column are completely selfish and that they play a one-shot game. However, now assume that the government fines defectors $5. Rewrite the payoffs in the table to account for the government's punishment of defectors. So again, we need to consider every combination of strategies. So let's start at the cooperate, cooperate cell. In this case, since no player is defecting, they're not fined by the government, so the payoffs remain the same. So the row player payoff remains the same at 10, and the column's payoffs remains the same at 10 as well. In the second case, row is cooperating and column is defecting, so row's payoff remains the same at 0. However, since column is defecting, his payoff decreases by $5 because he is being punished from the government. Right, so his payoff changes to 9 because 14 minus 5 is 9. Conversely, when we're looking at the cell where row defects and column cooperates, the row player is being punished by the government and the column is not. So the row player's payoff changes to 9 and the column's payoff changes to 0. And lastly, when both players are defecting, both players get punished. So the payoffs both change to -3 and -3 because 2 minus 5 is -3. Again, we want to know what each strategies would play. So again, let's look at when the column player plays cooperate, how would row respond? Would row play cooperate or defect given that column is playing cooperate? Row would play cooperate. Now let's see how row would respond when column plays defect, and row would play cooperate. Now assume that row plays cooperate, how would column respond? He would pick cooperate. Now assume that row plays defect, how would column respond? He would play cooperate. So in this case, we solve the prisoner's dilemma problem by fining defectors $5 and resolve the prisoner's dilemma. Okay, in summary, in this homework we employed the use of game theory to analyze a social interaction between two players. Given a specified game, you should be able to clearly define the strategies that each player would choose, be able to intuitively describe whether or not a specified game constitutes a social dilemma, and be able to modify the payout structure within a specified game that correspond to the three solution methods covered within this video, of which were altruism, repetition, and punishment. Okay, thank you. I hope this video was helpful.